Swayam Prabha. Digital India. Educated India.
So we've reached an important milestone in the course. So before I proceed further, I think it's important to summarize what we have learned so far. So I started the course by discussing the governing equations and the jump conditions at an interface. I derived the jump conditions rigorously. And we also studied the concept of Laplace pressure jump, where the idea of surface tension became clear. And we found that if you have surface tension and curvature at an interface, then there is a discontinuity in the pressure. Then we looked at problems in capillary statics. We concluded the topic of capillary statics by looking at the problem of capillary rise in a tube. Then we looked at problems in dynamics, where we looked at the problem of capillary rise in a tube, but now we looked at the evolution of the meniscus with time. Then we looked at free surface flows problems. In problems in free surface flows, I first derived the jump conditions. Then we looked at the Landau-Levitch dip coating flow. And then we discussed the shape of a falling jet. Now we can ask the question based on the last topic, which is the shape of falling jet, is what happens to this jet as it goes down? Questions like this basically form the basis of subsequent lectures. Now, to answer a question like that, we need to understand that what happens in an experiment is that when the jet actually comes down, it basically breaks up into droplets. We all know that. So for example, I am showing you here two sets of images. On the left panel, what you see is the initial formation of a jet. The jet has not yet formed, and you notice that further, you notice that these undulations, if I could just make them a little big, these undulations also are growing in amplitude. And eventually, they lead to breakup of this little filament into tiny droplets. But if you were to increase the flow rate sufficiently, then there will be a point where you have a stable jet, which eventually breaks up into droplets. Now, there is another interesting thing to note here, that you have an undulation somewhere in this region, and this undulation goes down. As the jet descends down, this undulation is carried forward, but at the same time it's growing, and it grows even further. It's becoming a lump here, and then a droplet, and here it's detaching from the thread. So this process continues, and what you're seeing here is the Plateau-Rayleigh instability, or the Rayleigh-Plateau instability. So Plateau originally studied this problem for a falling jet, and Rayleigh extended this analysis to study the stability of a filament, meaning a filament which is not actually moving. There's no velocity inside the filament. Now, I want to do the theoretical analysis, reproduce the theoretical analysis of Rayleigh. But before I do this, we need to understand the idea of stability. What does stability mean? And what are the common words that people use in stability? Stability forms an important subtopic in fluid mechanics. So we look at problems in stability in this lecture. Now this lecture is aimed at a physically inclined reader. For a more mathematically inclined reader, there are several excellent books on this topic, such as the classical book by Drazin and Reed, titled Hydrodynamic Stability, and so on. I will basically not be going into too much of mathematical detail, but focus on the idea of normal modes. How does it actually come about? When I say this idea of normal modes, many of you may not be familiar with it. So hopefully it's something that you'll be familiar with at the end of this lecture. But before we do this, let's look at a simple before we look at the fluid system, let's look at a mechanical system. So here I have a hinge support. Attached to it is a rod. Let's say it's a massless rod. And this is in a gravitational field G. Now, in this particular configuration, it's obvious that the mass would stay in that stable state forever. If you leave it undisturbed, it's going to stay in that state. So you can actually say this is a stable configuration, right? Let's look at another configuration. Now in this case, the mass is vertically up, so it's an inverted pendulum. But I have created a situation where the mass is perfectly straight vertically up. Again, in this case, if there was absolutely no disturbance, the mass would stay in its position forever. But we do know from experience that in the second case, the inverted pendulum case, any tiny amount of disturbance is going to make the pendulum fall. Now, in which direction it's going to fall? That depends on what perturbation or what disturbance has been given to the system. So any tiny amount of jerk that you give, the pendulum will either fall in the clockwise motion or it will take an anti-clockwise motion and it will approach the first state, right? So again, we have gravity in the second case as well, which is what is driving the system. And now you can actually say that there is an idea of a stable and an unstable. So you clearly know that this configuration is unstable, right? Now, is the first configuration stable? Most people would say yes, but we can actually derive another configuration or another state rather, which is to say that here's my hinge. I am releasing a mass from here. If I release a mass from that location, it would basically swing towards the vertical axis. But then if there's no friction, no loss of energy, total energy, because of, let's say, even air drag, then this pendulum would actually not stop at its vertical position, but continue to oscillate forever, right? So you can now conclude that without friction, theta equal to 0 is a neutral equilibrium. With friction, theta equal to 0 degrees is a stable equilibrium. Because the system would exhibit a damped oscillations in the presence of friction, and eventually it will appear, it will approach theta equal to 0 case. And theta equals 180 degrees is an unstable equilibrium. So I've introduced three words here: neutral equilibrium, stable equilibrium, or unstable equilibrium. Stable, to be more precise, this is stable asymptotically. Asymptotically stable equilibrium. Now let's look at a mechanical. This is a mechanical system. One can expand on this quite a bit, but we have seen three cases. A case where we have damped oscillations. The second one is where we have undamped oscillations. Undamped oscillations would occur for a neutral equilibrium. Now you see, I'm already using the word oscillations. Now the words like oscillation, when you apply to a fluid system, naturally becomes waves. So here's an example of a system where you saw waves were growing on the system on the interface and they become unstable, right? Now let's look at another classical problem in fluid mechanics, which every student in fluid mechanics would learn. This is a case of a fully developed flow in a pipe. So I have a long pipe of radius A, and so what would initially happen is, as the fluid enters the pipe, boundary layers form all along all along the walls of the pipe, and then eventually the flow would basically reach a fully developed state when the boundary layers merge at the center, and then you have this nice beautiful parabolic velocity profile. Let me write down the velocity profile. If I say that x is along the axis of the pipe, r is the radial coordinate, and theta is the azimuthal coordinate. So notice that I have written this down in cylindrical polar coordinates. If I write it down, I can say the velocity field, I'll call it as u, right? This velocity field would be sum capital V 1 minus r square by a square of I hat. And I can also write down the pressure P. Let's call the velocity with capital U. It will become clear why. The pressure P will be sum P naught minus 4 rho nu r by a square. Sorry, not r, x by a square. The pressure is basically varying along x. So this is valid for 0 less than r less than or equal to a. I have 0 less than or equal to theta is less than 2 pi. What about x? Now once it has reached a fully developed flow, it does not change anymore. So if the pipe is very long, then you can say that if the flow is laminar, and which means that the Reynolds number has to be sufficiently low, then you can say that the flow will basically forget about the initial condition and become a parabolic velocity profile. This last statement I said about the Reynolds number being low is not necessarily applicable for a pipe flow. Pipe flow cases like pipe flows are an exception, but most flows, as we increase the Reynolds number, they become turbulent. Now, if it's a long pipe and the flow has forgotten the initial condition, then you can essentially say x goes from minus infinity to plus infinity. Now this is a laminar flow. Now, can we see a laminar flow in an experiment? The answer is yes, if it is stable, right? If it is not stable, then you have to take great care to set up a laminar flow in an experiment. Why? Because it's not stable, therefore it is susceptible to any tiny perturbations, right? So such a flow is referred to as a base flow. A laminar flow for which we know the velocity field and the pressure field exactly, we can call it is a base flow or a base state. So what we want to do is we want to ask, is this flow stable or unstable? How do we go about asking that question? So we already have a velocity field and the pressure field which satisfies the Navier-Stokes equations. Now what we will do is introduce a perturbation. Introduce a small perturbation. Let's call it as u prime. And this perturbation can be a function of time, and a p prime, which can also be a function of time. The prime here denotes that it's a perturbation quantity. Now how do I get a perturbation? So if I know the total velocity field u, the perturbation, the total velocity minus capital U that I wrote down, the base flow. Similarly, pressure perturbation minus the perturbation, right? Now, typically when we start these equations, we start with a set of, what do we do? Original governing equations. The Navier-Stokes equations are non-linear. They're non-linear partial differential equations. Now we introduce these perturbations and then we get linear PDEs for the perturbations. Note that the base flow automatically satisfies the equations. Therefore, when I substitute the perturbation, which is of the form U bar minus capital U and capital P anyway don't matter because they cancel themselves out because they satisfy the equations. So what we end up getting are linear perturbations. Now, I get linear perturbations only if we assume that the magnitude perturbations are small. In other words, we will ignore all product of perturbations. That is, here I am writing ignoring product of perturbations. I am only retaining the linear terms. So, to go from non-linear PDEs to linear PDE, we substitute U bar is capital U plus U prime and P is capital P plus P prime. I have substituted this. Now I have got linear PDEs. Now once I have linear PDEs, I can assume a certain form of the solution. I'll tell you what the form of the solution would be. But if we assume a certain form of the solution, we go from linear PDEs to ODEs. Okay. So what we typically do in the stability analysis is we go from nonlinear PDE to linear PDE, and from there we get ODEs. It could be a single ODE depending on the problem, or several ODEs, coupled ODEs, which can be combined into a single ordinary differential equation. Alright. So from this we get what is called as the dispersion relation. Okay. Now, how do I go from the linear, how do I basically assume the formal solution? To achieve this simplification, we will assume we can Laplace transform in time we can take a Laplace transform with respect to time, Fourier transform with respect to x, and in this case Fourier series with respect to theta or in theta. Okay. Why am I allowed? This is for this particular specific problem. Why am I allowed to do that? If you notice here, from x goes from minus infinity to infinity, so it is natural to I could assume that any arbitrary form of the disturbance can be written in terms of Fourier transform. So for example, if something is varying in x, I could replace it in terms of sin kx and cos kx or exponential ikx. Theta is periodic, therefore I can assume it to be in terms of sin theta, cos theta, sin 2 theta, cos 2 theta, and so on, or in general sin n theta and cos n theta. I can generalize this and say it's e power I n theta. Time is going from time t equal to 0 and it's increasing, so I do a Laplace transform. Mathematically, how do I write? For example, if I were to write it for velocity, so my perturbation velocity, that's what I'm writing down here. This is x r, theta and time. X is along the axis, radial coordinate r, azimuthal coordinate theta. I have, remember the velocity is a real field, so I'll write it as real. Fourier transform in X. Let me write down the general form here first, and then we'll look at it a bit more carefully. Fourier series in theta, and then I have ds. I have a u hat. In general, u hat is a vector of r, k, n and s, exponential of st plus I kx plus n theta. That's what I have. Okay. So what I have done is I have replaced this. When we have a linear partial differential equation, we use a variable separable form of the solution. This is actually a variable separable form of the solution. The homogeneous side is basically x and theta. Therefore, I have Fourier transform of the Fourier series. In time, I have a Laplace transform, but the inhomogeneous side for me is basically radial direction. So going from r equal to 0 to r equals a. Again, I have to remind you that this is for this specific problem. But once you get a hang of it, you can apply this idea to any other problem. Okay. So now I have this general form. This is real, and therefore I can do this, or I could just write this entire expression without writing it as real something, plus add a complex conjugate. Okay. So this, what we have now got is, these are called the normal modes, or this is the now in general, one doesn't write such an elaborate expression, but uses a shorthand notation to simply say u prime of x, r, theta and t is just u hat e power st plus I kx plus n theta. Now I have not said what is s here. In this case, s can be s is a complex number. So s can be something like sigma plus I omega, or you can even write omega r plus I omega I, where sigma and I omega are just two arbitrary numbers, and sigma represents, if sigma is greater than 0, you can see that it will grow. So let me write that down. So we have e power st term essentially becomes e power sigma plus I omega of t, which is e power sigma t times e power I omega t. So I have e power sigma t, and I have cos omega t plus I sine omega t. So you can clearly see this part is always bounded. It's between -1 and +1. But the other part that you see here, if sigma is greater than 0, then e power sigma t grows exponentially. And if e power sigma t grows exponentially, u prime grows exponentially. We say such a state is unstable. We say flow is unstable. Okay. Now flow is unstable for some particular value of k and n. So in other words, what you imagine that you're fixing K and N. You could be fixing a flow parameter like a Reynolds number and ask what is the value of sigma that you get, okay, or the real part of S. The sigma is called the growth rate. I can write down other conditions. If sigma is less than 0, then e power sigma t decays exponentially. Okay, then implies u prime decays exponentially. So if for every value of k and n that you think of, for all possible values of a k and n, if you cannot find even a single sigma which is positive, or in other words, if every sigma is negative, then you say that the flow is completely stable. Okay. So that, remember, it has to be for all possible values of k and n, the value of sigma that you calculate. Okay. So only then flow is stable. But for the flow to be unstable, you just need one particular value of sigma to become unstable. Okay, to be greater than 0. Okay, and finally, if you have sigma is equal to 0, then we say this term does not matter. E power sigma t becomes equal to 1. This is 1. So you just have e power st just simply becomes e power I omega t. And you can see e power I omega t can be cos omega t and sin omega t. You have oscillatory solutions. Flow is said to be neutrally stable. Okay. So we have seen a criteria for stability which says, and we find that if you're assuming a form of the solution in this fashion, if you assume the normal mode form in this fashion, then all you require is the real part of S, or which is also called as the growth rate, has to be greater than 0. Okay, so that the system grows unboundedly, and you can say that it is unstable. Okay. Now you could have other possibilities as well. You could have other forms of normal mode. So what we have seen in this case, this particular way of doing it, this is sometimes also, this is not sometimes, this is called the temporal analysis. Why do we call it the temporal analysis? Because we are saying that I have a wave-like form in x that is coming from e power I kx. That's e power I kx. Remember here, the term that I'm highlighting here, exponential I kx that you see on the screen. So this term is cos kx and sin kx. So we are assuming wave-like solutions in x. We are assuming wave-like solutions in theta, e power I and theta. And we are asking, do these waves grow or decay in time? Okay. And because we are asking for grow and decaying in time, we refer to such disturbances as temporal modes, or we are doing what is called as a temporal stability analysis. You can even do a spatial stability analysis. So you would have the equivalent for that would be u hat of r x, r, theta and t would be something like u hat of r, k, n and s. Now the difference is, you now say it's something that is oscillating in time. So that is, I can say e power kx, but then I have an oscillatory behavior in time. So in time it's just a pure oscillation, or I can just say it is e power omega t plus n theta. That's better. Where omega is just an oscillation and k on the other hand can be complex. So here k can be a complex number. So k can be kr plus iki. So for x greater than 0, if kr is greater than 0, e power kx essentially becomes e power kr plus iki. Kr plus iki is the real and imaginary parts of k times x, and this gives me kr times x e power ikix. So what do I have is the wave would increase in amplitude as it descends, as it goes, as it flows. So this example that you saw here is an example actually of a spatial mode. You can see that the waves are actually growing as the jet is descending downwards, and this is a spatial system. Okay. Now for various reasons, I will basically stick to the temporal analysis for the Rayleigh plateau instability, because essentially I want to follow the analysis done by Rayleigh. A spatial analysis of the same problem was actually done by Keller et al., published in Physics of Fluids in 1972. That's a spatial stability analysis. So what do we achieve from doing this temporal analysis? Let's return to temporal analysis. What do I have in temporal analysis again? I have u prime is some u hat e power st plus I kx plus n theta. Okay. Now, you can actually, I can ignore, I have to mention one important point. Remember, we are working with linear systems now because we have assumed that this u prime is small, and therefore, when I substitute in these linear systems, I can have k going from minus infinity to infinity, n going again from minus infinity to infinity, but we can assume that each of these modes are independent of each other. So because it's a linear system, and the final state of the system is a superposition of all these infinite number of modes that I have. All right. Now, what we now have is a problem like this. If we were to substitute this form of u prime into my equations, what we obtained, u prime into the disturbance equations, and using the boundary conditions, we can obtain an eigenvalue problem. Eigenvalue problem for what? It's an eigenvalue problem of the form S, K and N. Remember, S, K, N appear in the normal mode form, and then we have some flow parameters. So we have capital V is a flow parameter. We have a material parameter, a geometric parameter, which is the radius of the tube, and then we have a material parameter, which is the kinematic viscosity. So we get an equation of this form. This is called the dispersion relation. So for some of you, you may not be very familiar with how do I achieve this. We will take an example problem. We'll do the analysis for the Rayleigh plateau instability, and hopefully it will become clear. So this is called the dispersion relation. It tells you how this complex growth rate or complex frequency S that you have here depends on the wave number k depends on the wave number k. This is wave number. You can say first k is an axial wave number and k is an azimuthal number, azimuthal wave number. Okay. In this particular case, n has to be an integer because you cannot have a wave, a bulge which goes around the circle and then comes back and not meet it again. So in other words, if you have a circle here, this is basically, remember we are working in the r theta cylindrical polar coordinates and my geometry itself is axisymmetric. If I have a bulge, I basically have to come back and meet the bulge. This is my perturbation. Okay. So I can imagine a jet. The jet could be, this could be the radius of the jet, the original radius, let's say A, and I'm perturbing the radius of the jet. So the jet basically becomes a little elliptical shape or any other shape that I want. But then you know that the jet has to close itself. Therefore, in the theta direction, these wave numbers are integers. And the idea is that the goal of this dispersion relation is we solve for S, the complex frequency, as a function of V A nu, or sometimes you can even say the Reynolds number, which is V into A by nu, okay, as a function of this and as a function of k and n. Okay, so for example, I could vary all possible values of n and k, and for a fixed Reynolds number, I can find out, is there any value of sigma which is greater than 0? Remember, what was sigma? Sigma was the real part of S. Okay. So if yes, then you say that the flow is unstable. So from this, I can make a map of this sort. You can say it's a stability map. Okay. So a stability map may look something like this. So you could have Reynolds number varied on the left side, and you can have sigma. Remember, S is equal to sigma plus I omega. So we know that if sigma is greater than 0, we have an unstable flow. And sigma is less than 0, we have stable. So typically for problems like this, not for the pipe flow, but certainly for the channel flow, when you have flow between two parallel plates, the Hagen-Poiseuille flow, the Poiseuille flow, what you have is, or the channel flow, what you have is a neutral boundary which may look something like this. So it means that there is this is of course varies from problem to problem, but there could be a critical Reynolds number in certain flows, where if you're below the critical, then the entire region sigma is less than 0. So in other words, this is a region where sigma is less than 0. So the flow is stable. But you can also have a region where sigma is greater than 0. This is unstable. And that sort of is in line with our intuition, which says that if you're below a certain Reynolds number, the flow is stable, but you have to push the flow beyond some criticality for the flow to become unstable. So hopefully in this lecture you got a sense of what we do in stability analysis. Let me quickly recap the key steps of stability analysis. So we could take an arbitrary flow which is laminar. It could be steady, meaning not time dependent, or it could even be steady. Such a laminar flow, we will call it as the base flow. Okay, this is my in this particular case, this is my base flow. Okay. Now we take such a base flow, we apply a small perturbation, we linearize the system, we go from a non-linear PDE to a linear PDE. Then we assume certain form of the solutions, so called the normal mode form of the solutions. These are called as normal modes. These form of solutions. So what we are doing, going from linear PDEs to ODEs, we are using what is called as the method of normal modes. And we use typically when I do problems, I will not write the real part or the complex conjugate because they are assumed to be taken into account. In any case, because physically a complex velocity field does not have any physical meaning. So we take only the real part. And then finally we get, after taking the normal mode form, the goal is to get something called the dispersion relation. Now this dispersion relation, if you're depending on the problem, the complexity of the problem, sometimes it can just be a simple polynomial equation for S as a function of other parameters, or it could be a transcendental equation. So one has to, it can vary from problem to problem. And now once you basically get this dispersion relation, we have to figure out a way to solve this dispersion relation for S as a function of K and N, and look at a stability map like this. Okay. If there is a control parameter in your problem, like the Reynolds number, then you can come up with a stability map, so that the stability map tells you what are the regions of stability and what are the regions of instability. So if you want to see a flow in a laboratory setting, you can only see it in a stable configuration. Note that you cannot directly set up an unstable flow in a laboratory. What you can do is set up a flow with a certain condition, and then disturbances will make the flow go to that unstable state. But you can't instantaneously set up an unstable flow in an experiment. But if you want to set up a stable flow, then linear stability analysis can be a useful guide. There are other advanced techniques here, which is basically, apart from temporal and spatial stability, you can have a nonlinear stability analysis, which is still an evolving field, but that will be too advanced for a course of this nature. So what we will be doing in subsequent lectures is we'll be looking at some problems in stability, particularly the Rayleigh plateau instability. I'll be doing the analysis that Rayleigh originally did, and then we'll be looking at stability of thin films. So I'll be using the method of normal modes in both those problems. The base state in both those problems are different, and therefore the normal mode form that we take also is slightly different. We will see that. Thank you.